Hello everyone, welcome back to my channel. Hope you all are doing good. Now we are going to talk about the complete understanding of how the linear regression works, and without delay, let us start with the topic. Let us understand simple linear regression in a more detailed way. So like we already discussed in our previous videos or previous sessions, a simple linear regression is a supervised type of algorithm. And I have already explained, in supervised type of algorithm, we knew the dependent and independent variable, and based on the behavior and the pattern, we are coming to a conclusion, okay, this could be the predicted value of the dependent variable. And how it works, we will understand in our further slides. So here, the simple concept, it is based on the relationship between two continuous variables. What is a continuous variable? If you are considering a person's details or a human's details, height is a continuous variable because that's a continuous numbers. Weight is a continuous variable. Then like take any other students. If you'll take a case of students, marks is a continuous number. Then what else we have? Marks, then again students' height, then the class name, classroom name, and all these things are your continuous number. However, at the same time, when I'm talking about the number of students in class, the number of cars passed at a single point of time, all those are your discrete variables, right? And let us dig more on that. And simple linear regression is a method or is a process where we are assuming the linear relationship between the two variables, the dependent and the independent variable. That means we will know how a independent variable is changing based on a single point of time as per the dependent variable. At a single point of time, how y is behaving with x, and based on that, all those data points which we have for a particular instance is going to create a linear relations or linear regression line, and that's how it's going to predict the next value of y. Then here the goal, like I mentioned, here the goal is to find out the best fit line. Best fit line is a straight line or the regression line where the differences or the errors or the residues are minimum. Let us go ahead to the next slide. So now we will understand how these things or the simple linear regression is getting derived or is getting converted. Or let me take you to the whiteboard to explain these things, like whatever we are seeing here. Let us understand that. When we're talking about simple linear regression, we will draw a relationship between two variables. So this is your independent variable, dependent variable, and this is your dependent variable, right? So this is your x, this is your y. Now what we will understand, so at a particular instance, how x and y are getting present in this play. So when we are talking about linear regression, suppose you have 10 independent variables and one dependent. Of course, the target variable will be always one, right? So this is your x, okay, this is your y. So when we're talking about linear relationship, first what is happening internally, this x and y relationship will happen for each and every data points. That means if you have 10 independent variable, it will first understand the relationship between each independent variable. Then it is going to combine it and it is going to tell you the predicted output. Now, so these are your data points. Okay, this is your, let me draw it with different colors so it will be easier. This is your data point. These are your data points, different data points. Just imagine that these data points in a 3D plane, how it's going to look like, right? I mean, that's how you need to imagine. So these are your data points, right? So these data points are staying in a scattered manner, right? Because we need to understand the regressor line. So for that, what exactly is happening? If this is your regressor line, consider that this is your regressor line. So first what it will do, consider that the first x it is taking, it will first understand the distance, or maybe it will start from here. Okay, it will start from here. Let me draw the regressor line from here like this. Okay, let me remove this one. It will be easier. Okay, just understand that this regressor line, okay, this is the correct regressor line. This is your correct regressor line. Now, if you see, this is your first point, okay, then this is your second point. So this second point is having distance from this line, right? It has some distance from this line. So this second point, to make and to put into this regressor line, the distance is called a residue or the error. To travel or to put that or to cover that distance, there are loss functions how we are calculating, and there are this gradient descents and all we are calculating. So how it is happening? So all these points which are in scattered manner, when we are creating or when we are applying the linear regression, the relationship is going to be, this point will come here, this point will come here, this point will come here, then this one will come here, like that. It is going to travel all these distance, and that is how it will create your best fit line. So this line, when these points will travel to this particular line, what is going to happen? The errors will be 0 at this point, right? The errors will be 0. That means it has very minimum or the very minimum or very less amount of errors will be present, and that's where a best fit line or regression line is there. And our formula for regressor is y equal to b0 or beta 0 plus beta 1 into x1 plus beta 2 into x2, like that. So here I have 10x, that means your the last value will be what? Beta 10 into x10. So let us understand. So when we are talking about beta 0, that means this is your intersection, right? This is your intersection. When I am talking about beta 1, what is going to happen? It's going to create an angle here. This is the angle it is creating, and this is the angle it is creating. So this angle is your beta 1. So like that, all these points will create some angle. This point will create some angle. When it is coming here, this point will create some angle. So all these angles are your coefficients. These are your coefficient factors to determine the linear relationship between the data points and the dependent variable. So these points are your y, right? These points are your y. So when I'm talking about y, this is your y hat. Like we have one original value or the actual value, and one is your predicted value, right? Actual value. And the predicted value, which is your y hat. This is your predicted value. So when we are talking about the relationship between those, we are actually determining the difference between the actual value and the predicted value. Actual value and the predicted value. And all we are doing is calculating the minimum errors throughout the process. Minimum errors between actual and predicted. And that's how we can understand, okay, the independent variables which we have, like this x1 and x2, all these values which is calculating with beta 1 and all, those values will be less, and the lesser these differences we will be getting, the better the model is going to be, or the better the prediction is going to be. So according to the concept, y minus y hat, the difference between the actual and the predicted should be always less. Should be always less. And this is how your linear regression works. Now let us go to the PPT. The same thing here I have shown, like we have y hat, which is a predicted value, b beta 0 plus beta 1 into x. So y hat is a predicted value, and if you'll see this image, the same thing I have explained there. Let me maximize it. So this is your intercept, right? This is your intercept. Then b1 is your angle. Then whatever the points we have, it is going to create the different kind of errors, right? Errors, then it will try to determine the distance. I told you it's a residual error. So like that, it is going to add up everything and it is going to give you the final predicted output. So you can see this is your observed value of y for xi, then this is your predicted value of y for xi, right? This is the observed value, this is the predicted value. Like that, it's going to understand the trend or pattern, right? Now, let us go ahead and understand the other factors. Now we are proceeding with the linear regression. Then what is the next step, guys? We are collecting the data. So when we are collecting the data, we are collecting the independent variable and dependent variable, and we are calculating the coefficients, right? The beta 0, beta 1, beta 2. Like I am talking about the internal process, what is happening, because when I am going to work with practical way, we cannot see all these formulas. It's just you have to understand how these formulations came into real life or they came into picture. So the coefficients when we are talking about is based on the ordinary least square method. Like whenever we are talking about this formula, this b0, b1 and all, how it is calculating, this is the way it is calculated. So when I'm talking about beta 0, it will take all value of y. Let me get the pen and so we have y, right? Consider that y has some 100 rows. Okay, y has some 100 data points. Similarly, x will be having 100 data points at the same time, right? And when we're talking about model training, we will definitely take 80% of train data and 20% of test data. So let us take 80 out of 100 and this one answer 80 out of 100. So how B0 is calculating internally? B0 or the beta 0 is calculating with the mean. That means it is going to add up all the y values, y1 plus y2 like that, all the values, and it will divide it by 80 minus b1 or the beta 1 value which will be there into the mean of like x1, x2 and x3 divided by 80. It's going to calculate like this. Then b1, how it is calculating? This is the way it is calculating. This is again another formula. xi minus mean of x into yi minus mean of y divided by xi minus mean of x, just square of it. The square of it. So here xi and yi are the individual data point and mean is the mean of the value. So these are the formulations which is happening on the behind the scene. Okay, and you don't have to remember these formulas, and you just need to understand the concept. For that only I'm explaining. So once it understand or it formulate the model, it understand the straight line trend, expected. After that, it is going to collect the data. It is going to understand the coefficients, beta 0, beta 1, beta 2. If you have 10 data points, it is going to calculate till beta 10. Then next, what is going to happen is, it is going to understand the regressor line or the best fit line. To understand that, what is the main factor here? It is going to understand the errors present in that particular data points. So for that, here I have shown one image. Let me maximize this image. So what is happening here else? So you can see this is your formula, this is a regressor line, and this, based on this formula, our regressor line is coming into picture. So when I'm talking about a particular point or the particular data point at a particular point of time, you can see this is one distance, right? X and Y hat. This is a predicted value, this is your actual value. Let me draw it. This is your Y, this is your Y hat. This point is your Y hat or the predicted value. So at particular given X, this was your actual value, this is your predicted value, and the distance which it covered, this distance, is your loss function or the cost function. And all these loss functions can be determined by different methods. We have mean square error, we have mean absolute error, right? And we have root mean square error. So with all those methods, we can understand exactly what is the error present for that particular data set, right? So this is your loss function, and that is how your best fit line comes into picture. So best fit line formula, if you will get questioned by an interview, then just simply say that it is based on a straight line formula, and where all the data points have minimum residue or minimum error, that is your regressor line or the best fit. Now, let us understand the next slide. So, we understood the best fit line. Now, the next criteria what we have to do, we need to calculate the loss functions. And to calculate the loss functions, we need to understand the optimal values of the parameters, like what is the actual value, what is the predicted value, like the way I have shown in the previous image, how the difference it is calculating at the particular point of X. And what it will do, it will define the difference between input value and the predicted value. And we have different methods, like I mentioned, mean square error, then mean absolute error, then R square, and all those points are getting calculated. There are calculations present to calculate the distances, and we will come to a conclusion that these have more errors or less errors. So simple fundamental is, the less amount of error present, or the less mean square error, the less mean absolute error, or the root mean square error value, the better that model is going to predict, because the error is less. The distance between the predicted and actual is less, right? So this is a formula. This is a generic formula for your mean square error, right? Now we will understand each and every accuracy method. These are called accuracy method, guys. When we are talking about accuracy, this is how we can judge our accuracies. So these are your different accuracy method to determine the predicted value. Now understand mean square error. So again, mean square error is a statistical method or the statistical way to calculate the average of all squared differences between the actual and predicted values. So what we are doing, we are taking the difference between the actual and predicted, we are squaring those values, then after that we are summing it up with the number of independent variables. The same formula is defined here. MSE is a mean square error, n is a number of data points. For example, if you have 100 data points, it is going to divide 100. Yi is your observed value, and or the actual value. Y is your predicted value, or the yi hat is the predicted value. And the same thing they have shown here in this image. to determine the positiveness only, they are actually squaring it off, and when because of that there is a chance of getting the model is getting overfitted, because when you're squaring it up, the number is going to come more, right? The residue or the distance or the amount is going to more if you have large amount of data set, correct? So to avoid that, we have further more accuracy methods, and when we are working with, in a practical scenario, the real time scenario, we need to observe all these accuracy methods and we need to understand which is giving the highest accuracy, and we will go ahead with that method. This image, if you see, so this image, if you see, this is your actual, right? And this is your predicted, and this is your regression line or the best fit line, and how the mean square error is getting calculated, the difference between y minus y hat or the predicted square of it divided by the number of data points or the number of independent variables present at that particular point of time. Then we have mean absolute error. Again, mean absolute error is again one more statistical way or the common metric to evaluate the performance of your model. This will help you to understand the accuracy of the model. How it is going to be calculated? So in the previous example or the previous slide, we saw that we are calculating the mean square error, and here we are calculating the absolute error by defining the absolute value or the absolute value of the differences. So here what we are doing is just a difference between the formulas. So here what we are doing, we are calculating the difference between actual and predicted, and we are getting the mode of it. Then after that we are dividing with the sum of the total data points. That's how your absolute error is getting calculated. And if you see the difference, if I'll ask you the difference between what is the difference between mean absolute error and the mean squared error, it's always going to be the mean absolute error is going to come less as y, because that is a square value, and it's not preferable for large data set because there is a high chance of the model, like it will give you the output as the model is overfit and all. So to suppress that effect, we are always preferring the mean absolute error. So in mean absolute error, there is a, it's a robust method of finding outliers if you're finding outliers, and it's a good method to use in your model. Here are a few differences which I am showing here. So like I mentioned, mean square error is going to get the difference between like it is going to get the square differences. Mean absolute error is going to get the mode or the absolute differences. So it will penalize large errors more heavily. Like if you square it up, you will get more number of errors, right? However, in mean absolute error, it's a robust method to find out the errors. And the impact is going to be again linear, because you are just getting a mode and all the errors are going to be coming nearer your best fit line. So these are again highly sensitive to outliers. Mean square error method and mean absolute error method is bit less as compared to the effect towards outlier is bit less as compared to mean square error. So these are your differences. Then we'll understand what is root mean square error. It's simple, guys. So we have calculated mean square error, right? We just need to get a square root of it. Why we are doing? We want to reduce the effect of the error. It's just for that purpose, and the prediction accuracy we are going to increase with that. So for that purpose, we are getting the root mean square error so that it will be coming closer to your best fit line. And this is your formula. It's the same formula, predicted minus actual, and it's a summation, like summation, then summation square of summation. Then after that, we will divide with the data point, then we will get the root mean square of it. So these are few points, important points which I want to explain you. So root mean square error, okay, is going to provide a single number, okay, like it's going to provide a single number that quantifies overall error of the model. And these errors are squared before averaging, and because of that, large errors is having very less impact, on your model, and when we are seeing the final score as compared to the other methods. And it is a better method or better approach to compare the performance between the different models, as and when we are comparing, it is like, suppose you have some 5 or 10 models, similar kind of models which you want to compare. How you can compare? So the variables which was used in one model and the variables which were used in the other model should be of same type, should not be of different type. RMSE might not be working in different kind of variables. It should be always working better in a similar kind of variables, and compare the errors of the similar kind of variables when we are comparing different kind of models. Then one more important factor which we are calculating, which is your R2 square or R square score. So R square tells you how your regression model fits the data. That means it is going to give you the percentage. We will understand in our next video how these things are getting calculated. So it is going to again understand the difference between the dependent and independent variable, and if R square is coming 100%, that means here actually the difference or the value is between 0 and 1. However, when we are calculating, we are just multiplying with 100 to understand the percentage of it. So if R square is coming 100% or the R square value is 1, that means it's a perfect model, and where all the variances are in a more balanced way. That means it is less variance. Then if R square value is 0, that means model is not able to predict, it's a failed model. Then if R square value is coming between 0 and 1, that means it's somewhat good. Like again, the accuracy should be more than 80%. I was always explaining you. So this is the factor which is the one which I am talking about always. So R square value, right? It's always a partial fit model if it is coming between 0 and 1. So here one example I have shown. Suppose if you are getting R square value as 0.9. So when I'm talking about 0.9, that means 90% of variation, okay, of the independent variable is getting explained by the dependent. 90% of variation or the variance of x, of y or the dependent variable is explained by the 5% of the independent variable. That means with 5% of data, it can understand the 95% of the output, right? And those 5% is due to the random errors or the residues or the differences and all, like between the best fit line and also that is what. And suppose you have a model, okay, and in future you are getting some requirement on adding up new variables or the independent variables in short. What will happen if you keep on adding the value? What is going to happen? It's going to be decreasing. Like not this, actually the adjusted R square is going to be decreasing. R square will never be decreasing the value. It will always stay same if we'll add new independent variable. However, there is a chance that it can cause overfitting, right? Because what's going to happen, the more and more number of variables you are adding, already the model understood the trend, and if you are adding new variable, again it is going to understand the existing trend plus the new variable. So as the model already understood the existing trend, suppose you have 10 independent variables, so those independent variables, it understood the trend and it is giving you the predicted output. Suppose you are adding some 2 more variables in that. So it's not like that it is not going to, understand the existing variable, right? It will take the whole 12 variables and it will predict the output based on that. So, however, it understood the trend of those 10 variables. There is a high chance that it is going to give you the highest accuracy, and the highest accuracy or the highest, like if the output you are getting 100 as compared to your actual value, that means the model does not understand anything, right? So that is to avoid that, like as R square value never decreases, to avoid that we have adjusted R square, and adjusted R square is good method for multiple regression. We will understand that multi-level regression or multiple regression we have, we'll understand that. So what it will do, whenever it is adding new variable to the model, it will, suppose it is not able to predict in a correct way, then it will penalize, and when it will penalize, it will reduce some of the amount of R square, and with that it is going to perfectly understand the accuracy, and the same thing here it was mentioned. So R square will always stay same or maybe increasing. However, when it is coming to the adjusted R square, it will always understand the trend of the variability between the different variables, or the variance it will understand. If you are adding up new variables, then it is going to tell you or it is going to penalize time by time, and it is going to give you the correct predicted output at the end. These formulas you don't have to remember, it's just you need to understand adjusted R square. Adjusted R square is for adjusted R square value is for the multilinear regression, where more and more the independent variables are more, and it is going to understand the trend and it is going to penalize. However, R square variable, it is not going to work better when you are adding more variables in future. Then we will understand the concept of overfitting. Overfitting I have already explained you. Here one example I have given. So suppose I am giving a particular question paper which has 10 questions, and I am going to give those 10 questions to that student, and whenever any exams are coming and those 10 questions are coming in those exams, or that student is appearing the exam, that those questions that student is able to answer 100%, because that student has memorized all the answers and is giving. But whenever it is coming the real examination, like the yearly examination or the half yearly examination, that student is failing completely. Maybe that student is scoring 30 out of 100, wherever like when the same question paper that student is able to answer 100 out of 100. So that's your overfitting problem. So what is the difference? So when I'm talking about the question paper with the 10 answers, that is your training data. However, the new question paper which that student is appearing in yearly exam, that is your test data. So the model, my point here is the student, here consider the student has to understand the concept, right? Before appearing for the exam, that student should not memorize the answers or should not memorize the questions, because questions will come different on each and every exam. It won't be same. Similarly, when we are feeding the data to the model, all independent variable, we are feeding the data. What exactly it has to do? It has to understand what is the nature of those data, how all those data points are getting coexisted with the dependent variable, or how those are linearly dependent, the co-relationship between them. They have to understand that. If they will understand that better, like the trends and the patterns, then they can be able to easily predict whatever the data you are giving the input further to the model. Because the more input, one more point is that the more input if you give to the model, the better the accuracy it's going to be. Because it is going to train the itself in a better way. So next time, whenever you are giving the more amount of data to the model, it's going to give a higher accuracy because it's able to understand the trend. So these are few scenarios on which actually the overfitting case will happen. If the model is very complex, so we have high degree polynomial regression. I will explain the polynomial regression. So polynomial regression, like I mentioned, is based on the number of degrees. Highest degree of polynomial regression used to take 2, not even 3. So to avoid complexity in the model, we always used to follow this linear regression trend. This is a simplest method to to apply in each and every case of model training, right? So if you have too many features, so if a model is complex, there the issue will come. If so many features are there, then issue will come. That's why we have feature importance coming into picture, right? Where we are reducing the features, dimensionality reduction point is there, where we are reducing the features. We are combining the features. We have feature engineering coming into picture. Then if you have very low amount of training data, then model cannot be trained well, right? So always remember the training data should be more than the validation, than the test data. Then if you have too many training iterations, like you're training the model repeatedly just to understand the trend, or just to make your to prove that okay, you are getting better accuracy. If you're training the model again and again with the same data, then there is a high chance of getting overfit. Then if your training data is having higher noise or a higher error or a higher residue, then that is not a recommended case for better model. So these are the few points to consider. So how to prevent overfitting? We have again these steps. You need to simplify the model. If it's a complex model, then you need to apply regularization technique. Again, we have so many algorithms for that. One is a lasso, and we have ridge, where we are penalizing on what? On the gradient, or on the slope, or on the m value we are penalizing, which will regularize the, or which will minimize the, or which will bend the line towards the regressor. Then we have cross validation. Okay, that's again one more method where we are dividing the data into multiple parts to test the generalization. Then more data, if you are training more data, it's going to be a good pattern. It is going to give a good pattern. Then early stopping is a concept of deep learning. You just need to understand that there is a concept where we are stopping the training the neurons, because their neurons will come into picture. So if you need to stop few neurons, like if the training or if the accuracy is not crossing or it's getting constant after one point, you should not train. So their early stopping point will come in case of deep learning. Then feature selection, again you have to have a good feature engineering concept when it is coming to the model training. So these are the points with which you can prevent your overfitting. Then we have gradient descent. What is a gradient descent, guys? Gradient descent is a point where the cost function is minimum. Suppose this is the example how your cost and weight relationship is coming. So how your model is getting trained. Okay, so this is a steps which I have shown you here, and let me explain other steps so it will be easier. So when we're talking about a straight line, right, what is the formula and what is the predicted? So we have mx plus c. So we have mx plus c. When we're talking about mx plus c, it will calculate the cost, and this is how we are calculating the cost. This is the formula for the rate of rate of, this predicted value with M, and this is the rate of predicted value with B. And this is how the formulas are. And once you will get the complete value, you will be able to know, okay, this is the value which you have to take and you have to multiply with the learning rate. So here alpha is the learning rate, and learning rate is a very constant value where we are telling the model that you need to learn in this rate, right? So you are calculating a new M and new B. So just understand that when the model is calculating this M and B continuously, and each M and B, the values are going to be decreasing. So until and unless the value, like one point will come where the value will stay constant. It will neither decrease or increase. So that point is your global minima. So what exactly is happening? Whenever the model is training itself, it is always based on, like I already said, that beta and the beta 0, beta 1 and all those things. So those are nothing but your M and C, right? So whenever you're talking about M and C, it's calculating those values repeatedly, and based on that, it's changing the position. The data point will change the position, right? Like this. Let me get the pen. So here the data point is getting changed from here to here. The position is getting changed because here the angle is changing, and here the angle is changing like this. Here one angle is there, right? Here one angle, here one more angle. So like that, the angle or the M value is changing, and the B value, the intercept, is also changing. So one point will come, okay, based on the learning rate it is changing. One point will come where the convergence is stopped. That means at this point, if you see this minimum point, the value will neither increase or decrease. The value will stay constant. These M and B will stay constant. And that is your global minima point, and where the error or the residue is none. And that is nothing but your gradient descent. And this is a kind of study, or this is a kind of algorithm which has been used in case of linear regression. Convergence theory, like I mentioned, it is used in gradient descent, where the optimal solution or the point or the the steps which is taking, right, the steps which is taking to come to the global minima, that point is a convergence point. That point is a convergence point. Or I can say that convergence theory is a process by which gradient descent will reach towards the minimum point or towards the optimal solution. Okay. Then we have global minima. Same logic. The point here, the point which we are seeing, that is your minimum point or the global minimum, where the cost or the error is very minimum. Of if you'll ask me, that I can say that is 0.00000 like that. It's very minimum. It's diminished. So that is what your global minima. Again, we have one more concept called local minima and global minima. Local minima is this one. Each point here is a local minima. One final point where the value is kind of negligible. That point is your global minimum. So all these points are a local minimum. Now we will understand stochastic gradient descent. So we have different kind of gradient descents. One is a batch gradient descent and another is stochastic gradient descent. So batch gradient descent is a smooth downward path, okay, which it will follow when the data when the M and C values are decreasing. It's very smooth. Whenever we're talking about stochastic gradient descent, it will follow the zigzag path or the path on which it will cross, or it will cover the downhill path. It's zigzag, but it is faster. So that is the only difference between batch and stochastic. Stochastic is faster, however the batch gradient descent is slower. and this is the formula. And like, are you getting a question on this? You will get question on this, and you can just remember this formula. It's just simple. We have the angle, or we have the slope. The new slope, it is getting calculated by taking the old slope and by dividing, getting the difference between the learning rate. This is a learning rate. Alpha is a learning rate, and this is your like the rate of the old slope with the new slope. So that is how it's getting calculated. So we have understood about the complete linear regression algorithm and how it works. We will understand the practical exam in our upcoming videos. Thank you. That is all for now. We will cover further topics in our upcoming videos. The topics which I am covering throughout this whole course is based on the interview point of view, guys. So understand, go through each and every video, make yourself clear on each and every concept, because basics is very important to understand according to me. So let us target on each and every topic, understand it. Any doubts, please reach out to me through community or comments. Start subscribing if you have not done that. Like, share your comments, share your feedback, share this channel link to all your friends and near ones.